The last section we want to tackle 9.2. And this allows us to introduce a new operation on vectors. So we have things like u plus v, u minus v, and I could have a times u. If a was a scalar, I could multiply it by a vector. But I don't really have a notion of vector multiplication. And so we're going to get something that sort of behaves like that here. And it is called the dot product. Now the dot product says if we start with two vectors, a1 and b1 for u, vector v with components a2 and b2, u dot v. So we don't say times or multiplied, we say it's dot. It's the dot product. There's a number of different vector products that can be studied. In this course we're just going to stick with this one, but we'll use the correct term for it. We'll call it the dot product. And what it is going to be a1 times a2 plus b1 times b2. So it's component-wise multiplication. So the first two components multiply together, the second two components multiply together, and then we add up the results. Notice, though, that this is two scalars, and I'm adding them up. The dot product takes two vectors, and it gives you a scalar. It gives you one real number. So, for example, if u is equal to 3, negative 2, and v is equal to 4, 5, u dot v, we start by multiplying the first two components together, so 3 times 4, and then the second two, negative 2 times 5, so we get 12, plus negative 10, positive 2. You could do this with ones that aren't written in the vector notation, but that are written using the unit vectors, so say x was 2i plus 3j, and y was 3i minus j, x dotted with y, 2 times 3 plus 3 times negative 1, 6 minus 3, we get 3. So the computation is pretty straightforward. We should be able to dot two vectors and just end up with a scalar. If you dot two vectors together and you end up with another vector, that's weird. There are a few properties of dot products that are kind of nice. One, it's commutative. So u dot v is equal to v dot u. That makes sense. Order doesn't matter for addition and multiplication, so order shouldn't matter for dot products. If you have some scalar and you multiply that by a vector and then you dot the result with another vector, it should be the same thing as if you took that scalar and multiplied it by the result after you dotted them together. So scalars can be factored out. If you wanted to take the sum of two vectors and dot them with a third, the dot product is distributive. That's kind of cool as well. So u dot w plus v dot w. And this is probably the one that gets used an awful lot. If you take the magnitude of a vector and you square it, you get the same thing as if you take that vector and dot product it with itself. I think this one is kind of the big one. This is the one that shows up an awful lot in calculus, particularly in vector calculus, sort of the stuff you do in when you're looking at calculus and its applications to physics. But the other thing that the dot product can help us with is situations when you've got, say I've got two vectors, u and v, and I'm interested in the angle theta between the two of them. The dot product can actually be used to help us solve that. It turns out that u dotted with v is equal to the magnitude of u times the magnitude of v times the cosine of theta, where theta is this angle in between the two vectors. Or, equivalently, with a little bit of division, since these are just scalars, we can divide by those, that's well defined. The cosine of theta is u dot v divided by the magnitude of u times the magnitude of v. So we can show an example of that. Say u equals 2,5 and v equals 4, -3. Find theta. So I'm supposing that these two vectors have been moved so that their origin points, or the initial points rather, are at the origin. And if I laid them both down there, what would the angle be between them? Well, the cosine of theta would be u dotted with v, magnitude of u, magnitude of v. So 2 times 4 plus 5 times -3 for their dot product. The magnitude of u is going to be the square root of 2 squared plus 5 squared. Magnitude of v, 4 squared plus -3 squared. And if we simplify that out, we're left with -7 over 5 times the square root of 29. So, to compute theta, we get the inverse cosine, -7 over 5 root 29, which works out to about 1.83 radians, or if you're doing degrees, about 105.1 degrees. Something else that I think is kind of interesting is, suppose you have two vectors which are orthogonal. Now that's also another way to think of them as being perpendicular. So, orthogonal, perpendicular. So, if u is perpendicular to v, well, the angle between them has to be 90 degrees, or pi over 2. So, cosine of pi over 2 is equal to u dot v, magnitude of u, magnitude of v. But the cosine of pi over 2, that's 0. Now I'm going to leave out this denominator because it's not going to matter. All that matters is that the dot product of these things is 0. And it turns out that if you have some perpendicular vectors, their dot product is 0. That's an if and only if statement. So I could check. Suppose that u equals 2, 1 and v equals -1, 2. U dot v is equal to 2 times -1 plus 1 times 2. That equals 0, and that implies that u is perpendicular to v. So, nice applications of the dot product. We can use it to start sorting out the angles between vectors. We can use it to figure out when vectors are perpendicular, and we will have one more lesson which will cover the last few applications of the dot product for this course.